Okay, good afternoon, everyone. My name is Michelangelo Mangano. This is my email. I'm a theoretical physicist. I work here in the theoretical physics department at CERN, and I also lead the LHC Physics Center at CERN, which is the body that somehow contributes to the interpretation of the data coming out of the LHC. So this talk will cover, well, as the title says, the open questions in particle physics. I will do so from a theoretical perspective, the perspective of a theoretical physicist. And of course, before discussing the open questions, I have to say something about the closed questions, namely where we come from. The questions that particle physicists address are, in fact, questions that have been asked by human beings since ever. How does the universe work? Where does it come from? And where is it going? And we can rephrase these questions in a more technical way, if you wish, as what are the ultimate components of matter? How do they move? Where move is intended in a generic sense. It means how they interact, how they influence each other's properties. And what moves them? Why do they behave the way they do? So, of course, when you sit down and try to answer these questions, you ought to be very ambitious because you really go to the core of what's happening out there in the universe. We're not touching equally difficult and certainly much more difficult questions like how does the brain work, where does love come from, and everything having to do with human life, but at the same time, everything else which is related to the natural world we try to encompass. So we did inherit, if you wish, from the ancient Greeks, philosophers, the task of explaining how the world works. It's interesting that it's not just the questions, but it's also the approach that we follow today, which is very similar to the one that was followed in the course of the centuries, and namely to identify few fundamental principles from which we derive the properties of all natural phenomena, both in the microcosm, at the, let's say, on a human scale. That certainly is what was concerning the ancient Greek philosophers, and the macrocosm on the universal scale, cosmological scale. We try to have similar rules governing both. We don't want to have a description of the very, very small and completely different rules to govern the very big. What has changed, of course, in the course of history is our assessment of the validity of a rule. We are certainly much more sophisticated, both in the tools we have available to explore nature and in our way of formalizing the rules of nature. So what I call here the epistemological criteria, which establish the completeness of an explanation and of our understanding. And I will be giving you an example of these right away. In common, again, between their way of thinking and our approach to particle physics is the identification of two categories, namely the components of matter, what we are made of, and the forces that control their behavior. These are the two objects we should focus our attention, and we believe that understanding these two categories, we have a complete picture. So this is one example of what I just mentioned before, and the example, you shouldn't take it as literally historical. It's made up by myself, but using concepts and ideas that are common and familiar to everyone, and they do have some connection with actual thinking. So once upon a time, people thought that there were four components. It was air, water, fire, and earth, and everything was made out of these four key components. And there were two kinds of forces. The forces acting on air and fire, that was a force pushing upward, and a force pushing downward, acting on the earth and the water. And this was satisfactory to the extent that people put forward these ideas. But then somebody a bit more cynical and critical comes along, performs a judgment of correctness and says, but then, how come that if a tree falls in the water, instead of keeping falling, it just floats? That clearly violates some of these rules. And then we make progress from that. Archimedes comes along and puts forward his principle, which is that all matter is pulled downwards. We don't have two forces acting differently. There is just one force that pulls everything down. On the other hand, it does so in a way which is proportional to the weight of individual bodies, and that is Archimedes' principle. A body immersed in water receives a push upwards equal to the weight of a displaced water. So there are several interesting aspects in this, let's call it revolution. Namely, we go from something which is, for example, includes two forces to something that only includes one. So it's a simplification. We are simplifying the theory. But this simplification does not necessarily imply that the new theory is simpler in the sense of being less accurate or more naive. So we can look at this as perhaps the first historical example of the unification of forces. And the first direct outcome of this unification is that now we can explain, we start explaining phenomena which are a bit more complicated and that, you know, this picture, simplified picture, was not able to encompass. We can explain, for example, wind, because hot water is warmer than, hot air is warmer than cold air. So it moves up. But then, of course, the space that it leaves has to be filled in by the cold air that comes along, and that, of course, generates the wind. So the lesson here is that simplifying things, unifying, identifying similarities that lead us to see the common source of two different phenomena allows us to make progress, and often leads to a more correct theory than the one we had before, via simplification. Now, the fact that nature should be described by a limited set of simple rules, so the grand scheme that I gave you a couple of slides ago, is not guaranteed. It's not a theorem, right? So we don't take it as itself a rule of nature. It's just a fact. It's a fact that follows from centuries of scientific progress. And physicists are always ready to give up even fundamental principles. We call them fundamental principles because we use them and we keep using them until they reveal some incompleteness. For example, in the 1920s, people were ready to give up something so fundamental like conservation of energy because some phenomena were observed in the first studies of radioactivity in which, as a result of some nuclear decays, if interpreted in terms of the particles that were known at the time, automatically that would have led to a violation of energy. And people were saying, well, you know, what do we know about quantum mechanics? What do we know about nuclear forces? This is a completely new field. Perhaps in this context, energy conservation is not valid. Well, it turned out that energy conservation is valid. For all we know, it's still valid today. In fact, it follows from even more fundamental principles, and at the time, just pursuing this direction led to the introduction of another fundamental particle, the neutrino, that was not known at the time, and that by itself was taking away the energy that was missing and that was misleading scientists in their interpretation. So the great success of this way of thinking is that indeed, starting from these assumptions and looking at the consequences of the theories that we developed, we do describe in an extremely accurate way and in a unified way all of the phenomena that take place in the laboratory and most of what we see around in the universe. Not everything, as it turns out. There are phenomena that we cannot reproduce in the laboratory, like, for example, the Big Bang or the cosmos as a whole. And if we start looking at the cosmos, we do find a couple of glitches in our theoretical framework. One is the existence of dark matter, which is particles. We know that they ought to be particles. It's not some other form of energy. It is actual particles. However, particles which have never created in the laboratory and which are totally unaccounted for in the context of our standard theory of particles. And we know their existence via astronomical, astrophysical, and cosmological observations. In fact, as you certainly heard many times, only about 4% of the amount of energy that we know has to be there in the universe can be accounted for by what we know and what we create in the laboratory. On the other hand, for these 4%, we really understand every single property. And then there is this 70%, which is not dark matter. It's what we call dark energy, and we call it energy because we know that it's not particles, because it has completely different properties than particles. It has the properties of an energy. And while for dark matter, we expect the explanation to be some particle that's still to be seen and that hopefully will be seen at the LHC, for dark matter, we really have no clue of what it is. So talking about open problems for particle physics, here is two. Now, I'm talking about the cosmos here, so why is that a problem for particle physics? Well, because we use particles to identify the fundamental laws of nature, but out of these fundamental laws, we can explain how particles interact with each other. And when particles are put together to form a large body, like a planet, a star, a galaxy, automatically these properties will reflect into the properties of interaction among these large bodies. Therefore, the understanding of cosmological phenomena has to rely on the understanding of microscopic ones, because it's out of the laws that govern the microscopic behavior of particles that we can describe what happens out there. So to understand the origin of dark matter and dark energy, we have to improve our understanding of particle physics. We do believe that it's there where we will find the answer. Once again, it's not a theorem, it's our expectation, it's what we believe, and we have good reasons to believe in that. So we have two levels. That's true of any field of science. We have what I call the level 0 questions. So these are questions like what and how. So questions that we ask when we are trying to understand how some phenomenon operates. It's a mechanical, if you wish, understanding of phenomena. In the case of particle physics, these questions are there fundamental building blocks? In other words, you know the history of atoms, nuclei, protons, quarks. Can we keep chopping up matter, or at some point we end up with some fundamental building block? If there are these fundamental building blocks, what are they? Are they the quarks we know, or is it something else? How do they interact? And how these interactions determine the properties of a universe. We start from a fundamental law governing the interaction between an electron and a proton. How do we get, you know, the whole chemistry, the whole functioning of a star out of these? So these are mechanical questions. And most of science, in fact, is stuck. Science beyond physics, like chemistry or biology or you name it, are stuck at the level of answering these questions. While I think that we have made a lot of progress on questions like these, and there is only a couple, in fact, of these questions that are left, and I will come back to those later. So in addressing these mechanical questions, and on the basis of experimental inputs and experimental evidence, theorists built what is known as the Standard Model. The Standard Model is a bit like the Lego set, the Lego games that you buy to your kids, where there are few very specific and well-defined building blocks of different sizes, but it's a finite number of them, and there are few very specific rules with which you can assemble them. And out of these, you can build objects of arbitrary complexity. So our building blocks are the leptons and the quarks. They're divided into 3 families. In other words, we have a set of these objects which are different from each other, but then this set is repeated 3 times. And the first of these sets is what makes matter as we know it, the matter that we are made of. So there are the electrons and the neutrinos on one side, that's the column of the leptons, and then there are the quarks of type up and of type down, which assembled in different ways make the proton and the neutron, which of course themselves will make the nuclei, and together with the electrons they will make atoms. So this family, we call it family, occasionally we call it generation, they are synonyms from our point of view, is repeated 3 3 times. These objects are held together or interact with each other through forces. By themselves, quarks and leptons would be idle, wouldn't do anything. There has to be something. They have to exchange something in order to react, to induce some process, some non-trivial dynamics. And this is what's done by interactions or forces. Again, for us, are synonyms. We use different words, force or interaction, depending on what the outcome of this force is. Forces lead, for example, to the Earth attracting the Moon, the Sun attracting the Earth, or the electron being attracted to the nucleus. This is gravitational and electromagnetic forces. They also lead to scattering, which means diffusion processes. This is what happens, for example, for an electron moving through a metal. It's not bound in any place. It's just moving around as soon as we put on a potential. The protons in the LHC, they're subject to a scattering process because they're not being bound to anything, but there is a force that steers them around the tunnel. And then, and this is perhaps less obvious, forces induce transmutations. Transmutations such as, for example, well, the emission of light, when we have an atom in an excited state, which means that the electrons are out in an external excited state, and the electron falls onto its ground state, and by doing that emits a photon, which is radiation, which is light. There is no apparent force. In other words, this is not a context in which we would be applying Newton's law, F equals to ma. We just observe a state going to a different state. Nuclear transitions, radioactivity are other examples of these transmutations, which are induced by the weak interactions responsible for radioactivity. So of these fundamental interactions, we know 4. There is gravity, of course. There is electromagnetism. There are the weak interactions, which I just mentioned. As it turns out, electromagnetism and weak interactions, in the same way of the first example of Archimedes, actually turn out to be unified into a single force, even though they have apparently very different properties, but they do originate from the same object. And then there is the strong force, which is what holds quarks together inside the proton, and then indirectly the protons and the neutrons together inside the atom, inside the nucleus. There is another particle which we don't classify as either a force or an interaction, and that is the famous Higgs boson. There is nothing wrong with a particle not being either a force or being a fundamental building block. As I said, we have that distinction because that's what we had for many years historically, and now, in fact, in several theories that go beyond this standard model, there are objects that it doesn't really matter how we classify them. What is important is that they do interact, so they do behave like building blocks, but at the same time they contribute to interactions among the other particles. So it could be that a particle is at the same time interaction and building block. So you can go through these tables and you can count perhaps a couple of dozen, a dozen of independent objects, and that's all we need. So it's a very simple picture. It becomes complex when we want to get numbers out of it. Each of these interactions mathematically is represented by some formula, and if we want to calculate, for example, how long it takes for some radioactive process to take place, we have to solve complicated equations. But the framework itself is extremely simple. We have a unity of the laws of interaction. We have those 4 different interactions, but their structure is very similar. They have slightly different properties, but the same physicists can understand all of them because they all follow the same pattern, and likewise the unity of the elements. All of the quarks, even if they have different masses and different properties, they have basically the same property, the same fundamental role. One important result is the uniqueness of the fundamental laws, namely the laws of physics, as we could establish, are the same in time and in space. That is a fundamental result, because if that weren't the case, we wouldn't, be doing physics at all. It's important to know that the laws that control the interaction between two electrical charges are the same here as they are in a faraway galaxy, because otherwise we wouldn't know what to do with the information that's coming from that galaxy. We would be making observations of the light coming from that galaxy, but if in that galaxy there is a different chemistry than ours, what do we do with the spectra that we observe? So the only way, in fact, that we can gain some information about, say, the Big Bang, indirect information about the Big Bang by monitoring the universe on a cosmological scale, is because the laws of physics have not changed for the past 14 billion years. Now, as always, we don't take for granted. We go out and we explore these. When we measure the light coming from faraway galaxies, part of these observations are for us to learn about some of the processes ongoing there. Some of those observations we can use as standard candles to verify that, for example, the strength of the electromagnetic couplings is the same here on Earth as it is on those remote galaxies. So we have experimental evidence that the laws of physics are the same across the universe and in time, across in time. So there are constraints on how we can describe mathematically the interactions between particles. These constraints emerge from, for example, Einstein's theory of special relativity, that no information can travel faster than light. That guarantees that that requires that we cannot have action at a distance. In other words, here I cannot influence at this point in time and space, I cannot influence something that's far away. That has to take some time before anything I do will have an impact on something that's happening far away. And when we turn all of these into mathematical statements and framework, the description of the fundamental interactions ends up really being something as simple as the Lego game. In other words, particles interact locally at one point, at most in clusters of 3. For example, here we have scattered the diffusion, the interaction between two electrons, and these two electrons are exchanging something which is a photon, the quantum of light, and the exchange of these one particle, the photon, is what gives rise to all of the phenomenology of electromagnetism and therefore to chemistry and all of this physics. So the classification of the Standard Model consists in, for each particle, whether it's a lepton, namely an electron or a muon or a neutrino or quarks, to define precisely how it interacts with the different forces, with the photon, with the W and the Z bosons of the weak interactions, and in the case of quarks, with the gluons. You can take these little drawings and you can assemble them, and you can create, in the same way that you can play with Legos, you can create arbitrarily complex processes. And to the extent that they can, an initial and a final state can be connected through all of these little wiggles and diagrams, that process is going to happen in nature one way or the other. And the mathematical representation of these interactions will tell us how often those processes will take place, how rare they are. It will tell us what is the lifetime, for example, of an unstable particle. So from these fundamental building blocks, we build everything that's around us, and we build everything that we see throughout the universe, that we see. So that leaves dark matter aside, because dark matter we don't technically see, at least not through light. So planets, stars, galaxies, everything is made out of these little things. This is one example. The proton is put together by taking two quarks of up type and one down type, and two down type quarks and an up type quarks make a neutron, and you can check that out of the elementary charges of those objects, you get exactly the numbers that you would expect. And out of these objects, we can describe phenomena, for example, a radioactive decay. When we have a nucleus decaying to a nucleus with a higher charge, an electron and neutrino, what is actually happening is that a neutron is turning into a proton, emitting the electron and the neutrino, But then if we look deeper inside, it's actually just an element of a neutron, namely one of the d down-type quarks that turns into an up-type quarks, emitting a W. And once this W has been produced, it must go into something else. It cannot just leave because it's very heavy, so energy conservation prevents its living forever. It has to decay, and the only thing that it turns out it can decay to is an electron and neutrino pair. So we look at the tables I gave you before. You identify an element, which is the transition between a down and an up quark and a W, the transition of a W with electron neutrino. You put it together, and you build this representation of radioactivity. And if we put in the numbers, the formula, we get an accurate description of all of the radioactive decays that we see in nature. We can calculate things using this picture. Processes like these, mediated by weak interactions, are really what controls and determine the universe as we know it. Because it's processes like those that at the very beginning, at the time of the Big Bang, gave rise to the different light nuclei for helium, deuterium, lithium, hydrogen, of course. So they defined the objects, the matter out of which stars later on in the course of the expansion of the universe were built. And inside the stars, these are exactly the processes that, by processing the light materials, produce the heavier materials, for example, oxygen, carbon, silicon, all the way up to iron. And when the biggest stars come to the end of their life because they finish processing through these weak interactions all of the fuel they have, gravity just pulls them in. That leads to a huge crunch followed by an explosion. In this explosion, all of these heavier elements, they go flying through the universe until they hit some cloud of lighter gas that's initiating the formation of a new planetary system. And they aggregate with this cloud, and they will form planets made out of iron, silicon, carbon, as we are. So those weak interactions are the basis of our being here. So what are the open questions of this level 0? Well, what are the particles forming dark matter? I already mentioned that this is one of the big mysteries, so we still have some what questions to answer. Now, we know that we are all made of matter, but we do know from the theory and, of course, also from experimental data that there is antimatter. We create artificially antimatter in the laboratory. How come that there is no antimatter out there in the universe by itself? Why does it have to be produced artificially? At the beginning of the universe, we believe that there was the same amount of matter and antimatter. Something must have happened to get rid of the antimatter, and what are the processes that, how did this happen is one of the big open questions. And then, of course, is the table of fundamental forces and particles that I gave you complete, or is there something else? What else, if any, is there that we have not been able to detect? So we still have something to address in these level 0 questions, but by and large, most of it is settled. And therefore, as a field, we are mature enough to start moving towards a higher category, a deeper category, if you wish, of questions, namely the why questions. If indeed there is only 3 families, why is that? Why are there 3 and not 4, 5, or 6? Why some particles have a mass while others don't? The masses we observe also are very different from one another. The neutrinos are extremely light compared to the electron, for example, to the top quark. Why is that? The gravitational force is very, very weak. It's 10 to the 40 times weaker than the electric force. How come? I mean, typically, all of the other forces we know within an order of magnitude have the same strength. And then, are particles really points, as we expect, or maybe they are extended objects? You probably heard about string theory, where particles are, in fact, extended string-like objects. They could be membranes. They could be extended in 2 dimensions. We don't know that. We don't even know, of course, why we live in 3 dimensions, plus the time. We could be living in 5 dimensions, for all we know. So where do we get these answers to these very fundamental questions? And, of course, you know, we can keep asking questions, and at some point you land on the unanswerable question, which is Why is there something as opposed to nothing? And clearly there is a long way to go. And that gives you a sense, this last question, of, in fact, how much terrain we have to cover, and perhaps the 5 billion years we have left before the sun blows up are not enough. So you are here because you're curious about what we do, and I wouldn't be discussing the open questions unless we at CERN here had a way to try to address these open questions, and the way we have is through the LHC and colliding protons. Now, the proton is, from the point of view of the chemistry, is a very simple object, because on the scale of all of the chemical processes, and certainly of the nuclear processes, it's just a point-like particle. A proton produced at the time of the Big Bang and a proton produced here at the LHC at CERN are exactly the same. There is no way that you can tell the age of a proton. A proton is a proton is a proton. So it is an absolutely unique and well-defined object. As we start looking inside the proton, though, there is an incredible jungle of objects living in it. And that is related to the uncertainty principle that tells us that if we look at a phenomenon, if you look at a state for a very, very short amount of time, we are allowed to find in that state objects that for a short amount of time, in principle, would not be, can live, even if they would lead to an apparent violation of, for example, energy conservation. So if we look at a proton on a very small scale, the first thing that we notice is that there are gluons, of course, holding the quarks together. And once we produce these gluons, as I told you before, each of these little diagrams, if you can plug them in a process, they will happen in some way. And so if the gluon can couple to a couple of quarks, it does so here, but then it can also do so once it's produced. And a gluon can produce a pair of any arbitrary quark, for example, the charm quark, the strange quark, or the top quark. If this state has a mass too large to be compatible with the energy that the proton has, it will not live very long. The uncertainty principle will force it to go back to where it came from. But if we look at the proton a very, very short amount, with a very sharp resolution, we do expose possible intermediate states which are as complex as the 3 original quarks plus some gluons plus additional quarks. In other words, the proton pretty much allows us to give access to all of the states that we have in our table of fundamental particles, and by being so rich is an excellent tool in order to produce possibly other states that we are not aware of because we never had enough energy to produce them, but that at the LHC, with the energy we have, could become visible. And that's why we use protons. Here I have a slide about quarks and the fact that we cannot actually see them, but I think I should move on because I'm running short of time. So this is a typical picture of what happens when protons collide at the LHC. We have a proton coming in from here, a proton coming in from there. As they get close to each other, the quarks start feeling each other's presence. It's like bringing two electrons nearby. They feel each other's electric field, and therefore they tend to do something. And the quarks will, for example, if they're brought to close enough a distance, they will just scatter away, like, you know, when you take 2 billiard balls and you scatter them and you send them one just in front of the other. So they will be deflected at a large angle. As a result of a slide that I didn't discuss before, what happens is that these quarks cannot just get liberated, but somehow they themselves have to turn into protons or to other stable particles, and they do so by the emission of many little gluons, which are always around because of what I told you a couple of slides ago. So the final state is a state in which the original proton gave out some of its energy, continues going in the forward region, but some of the energy it's lost will go into these fragments emerging at large angle and to be detected by our experiments. And in those fragments, there could well be new particles, because at the time when the two protons overlap each other, if it's not generic quarks, but it's some of the new quarks or some of the other particles that have been produced in this virtual soup inside the proton that interact, that's what will be liberated and what will be seen. This is a picture of the real life events from our experiments. In the last few minutes, I want to tell you something about the Higgs boson, because that's, of course, the big news from CERN. The Higgs, as you certainly read in the press, is the particle that gives mass to the other particles. The way this happens is close to what happens when light goes through a medium. As you know, if light goes through water or through a lens, it gets deflected. And it gets deflected because it interacts with the crystal, with what's in the water or what's in the lens. Now, this is a photon, this is light going inside a medium. What actually happens at the microscopic level is that the photon, as it goes in, it's absorbed by some atom. The atom gets excited, and then it gets de-excited, and the photon starts moving again until it hits another atom, which gets excited and then de-excited, and this goes on until the particle goes out. Now, this continuous interaction with the medium causes an apparent slowdown of the photon. The photon will always be moving at the speed of light, but the fact is that it's continuously interrupted by this interaction with the medium, which apparently, if we are just looking from the outside, it appears like the photon is being slowed down. So the Higgs is something very similar. With the Higgs, we are embedded in this state of this field that permeates the universe. It's as if we were inside the water and could simply just not get out of it. So as light propagating through water has to follow this, has to move slower because of the interactions, we, being immersed in this medium, have to continuously interact with it. And the result of the interaction with this medium is precisely what gives inertia to particles. So using, again, the language of our diagrams that I gave you before, if we have a particle, this particle exchanges and interacts with a Higgs boson and interacts with the underground medium. So the strength of the interaction of a given particle with the medium is what will determine the mass of a particle. So a heavier particle is simply a particle that interacts more strongly with the Higgs field, in the same way that a particle that has an electric charge much bigger than the electron, of course, will be subject to a much bigger force when it enters into an electric field. So, and this explains the different masses. It doesn't explain at a fundamental level the different masses, but it tells us what is the mechanism by which different masses arise. We still want to understand why the electron has the mass it has and the top quark has the mass it has. So this is something that's everywhere, and we are embedded in it. So it's like being inside the water, but by growing up, being born inside the water and growing up inside the water, you may not realize that you are inside the water. So a fish probably doesn't know that he is inside the water. And the way he can realize that he's not in the total vacuum, but he's immersed into a medium, is by, for example, hearing rumors, noises. And that's due to the fact that there are waves propagating through the water. So our way of checking that we are indeed embedded in this constant medium is to try to excite it in the same way that we can excite water by throwing in a stone and giving rise to waves, or in the same way that I can just knock on this table and turn it from something which is absolutely at rest into something that has a dynamics. I'm exciting a wave through this table, and this wave is transferred to the air, and a wave then propagates and reaches you. So exactly the same is what we do here at the LHC in order to search for the Higgs boson. So at the LHC, we're not searching for the Higgs field, but we are searching for these waves on the Higgs field, which is what we call the Higgs boson. Now, the Higgs boson is heavy, And whenever you want to produce something heavy, it takes energy, and that's why we need a machine bigger than the machines we ever had in order to produce it. If I go like this, you don't hear anything, right? So I have to give a strong push. I have to put a lot of energy in it. This is a typical diagram with which we represent the production of the Higgs, just to show you, aside from the details, but once again, even for the Higgs, we apply exactly the same picture I gave you before of putting together all of these little small diagrams. Here there is quarks from the proton, they emit gluons, and these gluons emit a pair of top and anti-top. The top is very heavy. The Higgs couples more strongly to heavier particles just because it gives a mass. So the mass of the particle is a measure of the strength of interaction of the Higgs. So you want to have a particle which is as heavy as possible for it to be able to produce this excitation of the Higgs field. So we select top quarks to do that, and then top quarks annihilate, they produce a Higgs, and the Higgs decays to Z bosons that decay to electrons and muons, which is what we observe in the laboratory. So going back to the open questions, what are the questions that the LHC is set to address? First of all, we want to firmly establish the what. Until recently, the existence of the Higgs boson was part of the what's. What gives mass to the particles, the Higgs boson? It's been discovered, so it's something that the LHC was one of the main goal of the LHC was to discover the Higgs boson. That's been done. We want to discover direct evidence for the particle that's responsible for the dark matter in the universe. Most of the theories that explain, a large class of the theories that explain dark matter predict that dark matter could be produced at the LHC, so we are actively looking for it. We're looking for possible new fundamental interactions. I listed the 4 interactions before: gravity, electromagnetism, weak interactions, strong interactions. We call them weak interactions because they're very weak. There could be even weaker interactions that we've not been able to see as yet. Weak interactions were discovered last century. In the course of history, people knew about electromagnetism. The theory of electromagnetism was developed in the 19th century. People knew, of course, about gravity, and that was about it, right? So weak interactions is something much later. It emerged when we had sophisticated experimental tools that start detecting radioactive phenomena. So there could be other forces which are there to be discovered, and of course which the LHC is looking for, and we could find that there are in fact more fundamental interactions. Likewise, there could be more generations of quarks and leptons, not just the 3 that we know of, but there could be more. We have good reasons to believe that there has to be only 3. There are very strong constraints on others, but they could have different features. They could not look like the generations we know. The same pattern could be different patterns, and there could be more, very heavy, and we're looking for them. We want to continue exploring this question of whether quarks and leptons are indeed point-like, and we keep exploring these by doing measurements on the diffusion, the scattering of quarks and leptons at higher and higher energies, because going to higher energies probes shorter and shorter distances. At some point, we may find that indeed the interaction properties are not consistent with quarks being points, and then we will have to start opening a new chapter in the history of our field. So that was the what. We also want to firmly establish the how. The Higgs boson is the particle that we believe is responsible for the mass of the other particles. I gave you an outline of how this mechanism works. We have to check it in detail. What the LHC has done so far is simply to observe the existence of the Higgs boson. That it exactly behaves as expected by the Higgs mechanism that explains how mass is taken is something that has to be done, and there could be again surprises there. Finally, out of this picture, complete picture that will come out of the LHC, there could certainly be other phenomena that are not expected. And in general, depending on what the answer will be to all of these questions, we could finally start finding our way into the more difficult questions, namely the whys. For example, obviously, if we find the fourth generation, or if we find that particles are not point-like, the question of why are particles point-like is not a good question any longer. We will have to give up that idea, and maybe we will give we will start believing much more strongly into string theory. So as you see, I think the particle physicist can be very proud, and it's justified some arrogance in claiming that we do describe what we see in the universe, but at the same time, there is still a huge amount of open questions. It's very deep questions. In fact, it goes into the range of the why questions. As I said, the how and the what questions, by and large, have been addressed. We do believe that we have a robust, solid, and coherent theoretical framework to make progress. But as I pointed out in that previous slide, with that final question of why is there something as opposed to nothing, it's quite obvious that this is a route that will take a very, very, very long time. The LHC will be running at least for another 20 years, possibly longer, and we are sure that we will benefit from each one of these years in making progress in our field, and even that will not be the end. So I will finish here. We will now have another 15 minutes, I guess, for questions. I will post the slides on my web page, which is there. If you have questions that you don't want to ask now, you can send me mail, and I will be happy to answer those questions. And if you happen to be a trail runner, I will be happy to meet you on some course somewhere on the Alps where we can discuss about physics. Thank you. Yes, can you press the button so that...
Yeah, one question I'd like to ask. Is a proton, if it was left alone, completely stable for an infinite amount of time, or can it decay?
For all we know, protons are stable. In the context of a standard model, there is no state in which a proton can decay. So you can start putting together all of those little diagrams, and there is no way that you can go from a proton to something else. So that makes it stable. Experimentally, we know it's stable, but only with some limit, of course, because we have not explored every single proton of the universe. The current best experimental constraints on the possible lifetime of a proton set its age at about, not its age, but its lifetime at more than 10 to the 33 years. Now, the age of a universe is 10 to the 10 years, right? So the probability that a proton produced during the Big Bang will have decayed in the course of the history of the universe is 10 to the minus 23. Okay, so it's very small, but we have a huge number of protons, and therefore they could have decayed, leaving signs that we would know. There are many theories, however, in which, beyond the standard model, some of the theories that we use to explain, for example, dark matter, etc., in which the proton, in fact, could decay with a lifetime which is compatible with the experimental limit. Incidentally, if the proton had a lifetime of 10 to the 24, more or less, years, which is already very long, right, because it means 10 to the 14 times the life of the universe, we would know it because we ourselves could not live, because we have so many protons in our body that even with such a small decay rate, those decays would induce enough radioactivity in our body that we would just die out of radiation. So that is one of the easiest way to set a limit on the proton lifetime. Question?
The gravity has an effect, sort of point-like, at the large scale. We can think of the center of mass of an object. But I've heard people talk about the theory that the gravity at an atomic scale, gravity we perceive at the macroscopic level may be an emergent property of something else, and that gravity at the finest level, does it have to be point-like in the way we think? Does the Higgs discovery and theory sort of answer that question one way or the other, or are we still unsure about whether gravity really does scale down from our perception at the macroscopic level to something in there?
No, the Higgs does not address that. And clearly the question of what happens to gravity at the scale, at the microscopic scale, is a very hard one, because certainly experimentally we cannot access that, right? Because the gravitational force is so weak that we bring together, you know, if we look at an atom or we look at systems like that, force is only 10 to the minus 40 contribution to the interaction, and we don't have experimental precision to detect these effects. So all of the speculations on gravity at those, in those contexts are purely theoretical, and of course there are many ideas on what could happen. There are, for example, these ideas related to the possibility that there be extra dimensions at a scale of the order of the inverse of a TeV, so scales that could be probed at the LHC, in which all of a sudden new dimensions would open up and gravity would have access to those dimensions, so the gravitational force would not distribute itself over 3 dimensions, but over 4 or 5 dimensions, and therefore behaving in a very different way. That could have implications in our experiments, but certainly not otherwise in a lab. But the canonical gravity, yeah, we extrapolate it to the short distances that we can create, and it's not expected to give any surprise. And the Higgs doesn't help in this direction. You see, the Higgs deals with a mass. Gravity deals with energy. So Newton's law, gravity is proportional to the mass, but the actual gravitational law is general relativity, and their gravity is sensitive to energy. So it is really a very different object than the interactions of the Higgs boson. Question?
My question is, would it be correct to say that once that the Higgs boson is discovered, then the standard model is already complete, and then it is a closed theory, and then it does not need of any other, let's say, I don't know, forces or whatever, and then what would be the role played by gravity that is like outside? So there is no need of a unification of all forces to have a general theory?
Yes, technically it's correct with the discovery of the Higgs boson, and if we verify that it behaves the way it should, then in principle the standard model is a complete and closed and consistent theory. But we know that there has to be something beyond it. For example, dark matter. Dark matter does not fit within the standard model. You can look at the particles that exist within the standard model, both elementary as well as objects that you can build out of the elementary building blocks. There is just no way that the standard model can explain dark matter. So that forces on us to look for something beyond the standard model. And that's why people always reason in terms of physics beyond the standard model. And of course, ideally, as we move beyond the standard model, at some point we would like to bring in gravity as well, because in fact gravity lives as a separate object, and it's very likely that the theory that will explain, that will take us beyond the standard model, will also incorporate gravity. That's the case of string theory, for example. But string theory is still not a theory which is sufficiently well formulated that we can actually use it in practice, right? It doesn't make sharp enough predictions that we can use it. Question up there?
Do you hear me? Okay, yes. I have a question about basic and probably very formal about the reason why Higgs was introduced in standard model, that he is the giver of mass to all other particles. That's the definition of Higgs and Higgs field. Now, he is the giver of mass to all other particles. Now, but he has mass. What gives mass to Higgs in this theory?
Yes. Now, in the Higgs mechanism, the Higgs gets mass from itself because it interacts with itself. And so that's the answer.
But what is the coupling?
The fact that the Higgs gives mass to all of the particles, that is technically incorrect, even though that's what's seen everywhere, right? For example, dark matter even though it will be a particle, a legitimate particle, but dark matter does not get its mass from the Higgs mechanism. The Higgs I'm saying this because I know you and I know that you would understand. The Higgs mechanism is necessary to give mass to particles whose mass breaks electroweak symmetry. So the W bosons, the quarks and leptons, because the mass of quarks and leptons violates electroweak symmetry. But if a particle mass does not violate electroweak symmetry, then it can get mass from something else. The gluinos, the quarks, all of these supersymmetric particles that we are looking for, so new particles beyond the Standard Model, they will not receive their mass directly from the Higgs boson, but they can just have it as a parameter. Like in the same way they have a charge, we can give a mass to the gluino. They get it from supersymmetry breaking, so from other phenomena.
And how do we measure the self-coupling? I mean, what does, when Higgs interacts with himself, what can we see?
Well, there will be processes in which you create a Higgs, which is very much off shell, at a mass of twice the Higgs itself, and then it decays to 2 Higgses. That is the mechanism. Question up there.
Yes. There were theories that dark matter might consist of free-floating neutrinos in the space. According to your speech today, these theories aren't valid anymore. Can you explain something about that?
Yes. No, I didn't say that they're not valid. I said that most of the theories that explain dark matter, most of the theories in which there is dark matter candidates, those candidates could be seen at the LHC, but not all of them. If, for example, it's neutrinos that form dark matter, then of course those we would not be able to see effectively at the LHC, even though they're very light, but it's just the production that simply wouldn't work. And now cosmological evidence tends to make the interpretation. I mean, neutrinos are a component certainly of dark matter, but it's a very, very small one. It cannot be the dominant component. There are other particles, for example, axions, which are very, very light particles, which interact very, very, very weakly. And again, there is no way we could possibly see those in the LHC. And that is a possible explanation of dark matter.